Heidi ho everyone, my name is Max Joyce here with Physics 2212, lab number 3, circuits. As always, the first thing we're going to start with is an overview. We're going to do an introduction. We're going to talk about some equations very briefly. We're going to do the experiment. We're going to draw some conclusions. Alright, so going over this introduction first, I'm just talking about them concepts first. So we're dealing with the loop rule, the node rule, and Ohm's law. So of course, loop rule is change in electric potential is closed in a closed loop is zero! Exclamation point. The node rule is nodes have the same output of current going in that they have coming out. Should have put an exclamation point there because it's just as important. And then we have Ohm's law, relates resistors, resistance in ohms, their current in amperes, and change in electric potential. So essentially this is where we get the equation delta V is equal to I times R. Lastly, the purpose of this lab is to examine the behavior and predict circuits containing parallel and in-series resistors and capacitors. Alright, so going on to part 1 of our experiment, this is when we're having a pretty simple circuit, 2 batteries, 2 resistors, we're adding 2 ammeters to read the current. So after we did the equations shown on the left and plugged in some values, of course we used 3 for the EMF. Resistor 1 was 47, resistor 2 was 100 ohms respectively. And then of course we could predict the value of I that we should see in these ammeters, and of course because of these resistors being in series, we know that they should have the same current value because it's a property of in-series currents that they share current in and current out. You can essentially combine them into one singular current. Alright, so what we found out was that our predicted value through calculations was 0.02 amps, and our reverse value, I don't know why I put reverse, but our actual value was 0.02 as well, as you can see by the slides, or the picture. Alright, so going on to the next part, we had to use a voltometer. Alright, so on this voltometer, we just had to plug it up, essentially, and look at the volts when we open the loop. And of course, because we open the loop, no current is moving through, so the voltage will be the same because there's no current running through it, so there's no change in delta V, so our volt reading should be 3 volts, which is all our electromotor forces, which come from the batteries, each 1.5 volts each. So when the loop is closed, remember that, the ammeter reading is 0 amps because the loop is not closed. If we're to close the loop, at that point, it'll be different, as you will see in the next part. So talking about the loop rule again, this is when our things close. We're once again recording current. So from A to B, we have 3 volts because we're going across the battery, gaining electric potential. B to C, we're just moving through a wire, so we're not going through any with things, so 0 volt. From C to D, we have negative 0.96 delta V. This is because we're moving through a resistor, so we're losing voltage. And then D and E, of course, is just a straight or short wire, so we're not losing anything. E to F, we move through the bigger resistor, which has more resistance, so we lose more delta V. And at that point, we're out of voltage, so everywhere else has 0 voltage, delta V, and it's going to be at 0 volts anywhere until we move right across that battery again and gain 3 volts potential. Alright, so this is our graph that we made. This thing I drew is in the blue. This is really what I just explained. It's going to be linear, and then it's going to be constant because there's no change. This is just straight from the graph. Alright, so actual resistance values, we got this from actually using calculations that we received for the volt and showing the diff and showing the resistance and finding resistance. So of course for the 47 ohms resistor, it actually had 47.95 ohms of resistance. For the 100 ohms resistor, it had 102.5 ohms of resistance. The resistance of the wire, of course, had 0. Resistance of the ammeter had 0 as well. Sorry, that's a hard word to say. Alright, moving on, we're looking at this RC current now. We're adding in a light bulb and a capacitor. The light bulb, of course, is just a resistor, and then you can see the capacitor there. So all that we're doing is looking at the time this capacitor takes to, the light bulb that takes to light up with only the battery, and then also, how long it takes to lose its light, and then how long it takes to light back up with the capacitor discharging. And those are shown below. As you see with 20 ohms, it's about the same. Alright, so moving through this really quick, this is the 30 ohm light bulb thing that we found. We found that our RC value was 5.9. I won't bore you with the details of this. We're just using the standard procedure inside of the lab. And lastly, but not least, we're wrapping up with some additional questions. The what if question, I'll let you read this, but essentially actual emitters have resistance, so that delta V for the emitter would be non-zero. And that goes all the way back to that graph that we showed and those values that we found for delta V. And then the second what if question is the capacitor would change instantly without any resistance. So, excuse me, was charged instantly without any resistance. Because that current is going and that voltage is going straight into the capacitor. And in real life, resistance slows down the charging process.